Hi, folks. So this is to remind you that nominally session will stop at 4:45. And however, knowing what has happened before, and the bus driver said that the two buses will start waiting out there at 5. And they will depart no later than 5:20. So no matter how late this is, they will depart. Okay, so
welcome to IOPs and Succinctness session. The first talk is holographic snags for P and batch NP from polynomial hard along with errors. And Susumu will give the talk.
All right, so thank you for introduction. So I'm Susumu Kiyoshima from NTT. So this talk is about the succinct non-interactive argument or snag. So let me start from their definitions. So in snag, we have 3 algorithms, the generator, the prover, and the verifier. The generator sample a common reference string, or CRS, and makes it public. And given the CRS, the prover sends the proof to the verifier in a single message. The security requirement for snag are completeness and soundness, where as usual, the completeness requires that when the statement is true, an honest prover can convince the verifier, and the soundness requires that when the statement is false, any polynomial type cheating prover cannot convince the verifier with high probability. And in addition to these 2 security requirements, for snag, there is also an efficiency requirement for succinctness, which roughly says that the proof length and the verification time are very small. And in this work, we consider snag for a certain subset of the NP, and in particular snag for P and batch NP. In snag for P, the statement is an instance X over language in P, and it is considered true if a predetermined deterministic polynomial Turing machine M output 1 on input X. Regarding succinctness, the minimal requirement is that the verification time is much smaller than the running time T of the Turing machine M, which guarantees that the verifier does not need to run the Turing machine by himself. And usually it is required that the verification time is polylogarithmic in the running time T of the Turing machine M. In the case of snag for batch NP, a statement consists of a Boolean circuit and a bunch of input to circuit, x1 to xk, and it is considered true if the circuit and each of the input constitute a true instance of the circuit satisfiability, meaning that for each input xi, there exists a witness wi such that the circuit output 1 on input x1 and wi. So regarding succinctness, the minimal requirement for the case of snag for batch NP is that the proof length is sublinear in the number of inputs k, which means that the proof is not a simple concatenation of k witnesses. And usually it is required that the proof length is polylogarithmic in the number of inputs k. It is known that snag for both P and batch NP are very powerful and useful for many applications. And it is also known that they can be achieved under standard falsifier assumption, such as the learning with errors assumption, the decision linear assumption over bilinear groups, and the substantial hardness of the decision Diffie-Hellman assumption. Now, let us consider whether in snag we can make the verification time sublinear even in the length of the statement. So in particular, in the case of snag for P, the goal is to make the verification time sublinear in the length of the instance X. And for the case of snag for batch NP, the goal is to make the verification time sublinear in the total length of K. So clearly, this is in general impossible to achieve because the verifier at least need to read the entire statement. But actually, it is known that this is possible to achieve if the verifier is given as a statement in a pre-processing format. For example, it is known that in some of the existing schemes, the verifier can be sublinear if it is given a short digest of the statement, which is created honestly before the verifier is given the proof. Now, the target of this work is a holographic snag, which achieve sublinear time verification by considering a verifier that is given Oracle access to a encoding of the statement. So instead of considering a short digest of the statement, in holographic snag, we consider long encoding of the statement, and the verifier reads only a small part of the encoding to achieve sublinear time verification. Recently, holographic snag have been used as a building block or as a cryptographic object. And in particular, they have been used to obtain two-round argument proximity, three-round zero-knowledge argument, and probabilistically checkable argument. Very roughly speaking, they are useful as a building block because in the existing scheme, the encoding of a statement has additional nice property, such as being information theoretic and locally testable. So at a high level, being the information theoretic is useful to obtain round optimal protocol because if the encoding is information theoretic, we can encode the statement without sampling any cryptographic object as a setup. So we can say one round. And being locally testable is useful to obtain maliciously secure protocol because if the encoding is locally testable, the verifier can detect maliciously created encoding by making a small number of queries to the encoding. And in this work, we gave two holographic snag under the learning with their assumption. So one is for P and the other is for batch NP. And in both cases, we achieve good asymptotical verification time. And in particular, in the case of for P, the verification time is polylogarithmic, not only the computation time T, but also the length of the instance. And for the case of snag for batch NP, the verification time is polylogarithmic in the number of inputs, K. So prior to this work, holographic snag with such verification time is known as the designated verifier setting or under the sub-exponential hardness of the learning with error assumption. So the contribution of this work is to obtain such snag under the publicly verified setting and under the polynomial hardness of the learning with error assumption. And as application of a holographic snag, we use an existing transformation to obtain a public coin 3-round zero-knowledge argument from a slightly superpolynomial hardness of the learning with error assumption and the keyless multi-collision resistance function. So prior to this result, even though a private coin 3-round zero-knowledge argument are known from such assumption, public coin 3-round zero-knowledge argument are known even when only when the LW is sub-exponential hard. So there is a certain gap between existing 3-round public coin 3-round zero-knowledge and the public coin private coin zero-knowledge. And the contribution of this work is to close this gap by showing that the slightly superpolynomial hardness is sufficient for LW, even for the case of public coin 3-round zero-knowledge. So this is our result, and in the rest of this talk, I will explain how we obtain holographic snag from the learning with error assumptions. So our starting point is a recent non-holographic snag for P and batch NP that have been obtained from the learning with error assumption. And what is important to us is that these non-holographic constructions are non-holographic only because the verifier needs to compute the short digest of the statement. So this means that we can convert this non-holographic construction to a holographic one if we can somehow let the verifier obtain the digest of the statement in a holographic way. And since, of course, the prover does not necessarily compute the digest honestly, we need some kind of mechanism where the verifier can check whether the digest is created honestly or not. So, okay, yeah. So the natural approach is to delegate the computation from the verifier to the prover. And the main technical contribution of this work is is a holographic snag for appropriate set hash computation. And in particular, the hash computation that has been used to obtain the digest in the non-holographic construction. And we combine our holographic snag for hash computation and the existing non-holographic snag for P and batch P to obtain our holographic snag for P and batch N. And more concretely speaking, we construct holographic snag for two types of hash computation. So one is the macro hash computation, which we use to obtain a holographic snag for P. And the other is for summary extractable hash computation that we use to obtain a holographic snag for batch NP. So unfortunately, I don't have enough time to explain the detail of these two constructions. So we just give some key point of these two constructions. So regarding the holographic snag for summary extractable hash computation, one of the key points is that for our purpose, it suffices to achieve a weak soundness notion, which is defined carefully based on the definition of summary extractable hash function. So this is where we use the fact that we focus on the computation of summary extractable hash function. So very roughly speaking, it is weak in the sense that it does not guarantee the correctness of the global hash computation, but instead it only guarantees that the value we can extract from the digest using summary extractability must be consistent with the long input that has been that is supposed to be the pre-image of the digest. And another key point of our holographic snag for summary extractable hash computation is that to achieve holographic verification, we consider recursive construction where each recursion depends on a small part of the encoding. So in particular, each recursion can be verified by reading only a small part of the encoding. So we can achieve sublinear time verification in a holographic set. So regarding holographic snag for macro hash, we construct it by relying on the simple structure of the macro hash computation. So the detail can be found on the paper. So please check the paper if you are interested. So in conclusion, the main result of this work is a holographic snag for P and batch NP from LW. And as application, we give public point 3 round 0 knowledge from weaker assumptions than before. And by using this result, we close the gap between existing public point 3 round 0 knowledge and the private one. So this concludes my talk. So thank you very much.
Any question?
Thank you for a great talk. So I'm interested in what is exactly your soundness notion of the holographic snark for P? Because I know for like these digested RAM snark for P, it's only like you cannot prove two contradicting statements for the same hash. And now you have this like oracle access. So how can you like what your soundness exactly is?
So even though the verifier has only oracle access to the statement is already fixed. So the soundness is standard, like the fixed. If the fixed statement is false, then the verifier cannot, as a prover, cannot give up accept proof.
Okay, thanks.
You got a similar result from the bilinear maps or DDH, which we know non-holographically. Is there a fundamental problem, or what can you say about that?
I have not considered well, but now we use LW-based correlated interactive hash function to so that we can we can handle any like battle relation. So in the DDH-based construction, the class of battle relation we can handle is limited, and I'm not sure we can handle it. So I'm not sure this is the fundamental or not, but I have currently no idea about it.
Any other quick question?
So what this is
holographic snarks for Merkle hash also requires no signaling property or?
No signaling property. So the security proof we use is very similar to the, non-signaling type approach, but I'm not sure it is essential or not.
Okay.
It's time to move to the next talk, so let's thank them again. The next talk is chainable functional commitments for unbounded depth circuits, and Russell will give the talk.
Thanks for the introduction. So my name is Russell, and today I want to talk about chainable functional commitments for unbounded depth circuits. And this is a joint work with David Bauer, Dario Catalano, and Dario Fiore. So first, let me give you some motivating applications of functional commitments. And so the motivating application is verifiable computation, or VC. So we have two parties, the client and the server. The client delegates the circuit gamma to the server, and then subsequently the client wants to evaluate this circuit gamma on some data sets, xi, and so they send this data set xi to the server, who computes gamma of xi, which yields yi and sends the output back, together with a proof pi certifying that the gamma of xi is indeed yi. So as usual, we want a VC scheme to satisfy completeness, soundness, and efficiency. The completeness says that if gamma of xi is indeed yi, then the proof should go through. And soundness is the converse, which says that if the proof goes through, then indeed gamma of xi is yi. And finally, for the VC scheme to be non-trivial, we want it to be efficient in an amortized sense. So namely, the time needed to verify the proof is faster than the time needed to compute gamma of xi, assuming that the client performs a one-time preprocessing of gamma. So next, let me tell you what a functional commitment is and how we can use it to build a VC scheme. So a functional commitment is a tuple of 5 algorithms: set up, preprocess, commit, open, and verify. And so to use this to build a VC scheme, the client does the following. So first, they preprocess the circuit gamma with respect to the public parameters, which use this PP gamma that they keep for themselves. And they send this circuit gamma to the server. And later, when the client wants to compute gamma of xi, they use the FC scheme to commit to xi, which yields a commitment com I and sum of serial input ox I. And they send this dataset xi and ox I to the server, who computes gamma of xi as usual. But now they also run the FC opening algorithm on the circuit gamma and then ox I to yield an opening proof pi I. Okay, so in terms of security, we want an FC scheme to satisfy a weak security notion called the evaluation binding, which says that it's infeasible to open gamma and the commitment to two different outputs, yi and yi prime. And note that this security notion is rather weak because it says nothing about whether yi and yi prime are indeed gamma of xi or not. It just says that they cannot be different. Okay, but nevertheless, it can be shown that this implies VC soundness, because if the server were to give us a valid proof for yi, which is different from gamma of xi, then the client who computed the commitment honestly themselves can honestly open this commitment to gamma of xi, which by assumption is different from yi, and then we break the evaluation boundary. And also to yield to get an efficient VC scheme, we want our FC to be succinct, meaning that the time needed to run the verification algorithm is sublinear in the size of the circuit, description size of the circuit. So another motivating application is to bootstrap a snark. And in the previous talk, you already learned what a snark is, so I'm not going to repeat. So in order to construct a snark for all NP statements, it suffices to construct an FC scheme for, let's say, quadratic polynomials. And then we equip this FC scheme with a special purpose snark, which is only used to prove the well-formedness of the commitment, but nothing about the relation. And this whole construction is, in fact, the snark for NP. So the rationale of doing this is that although we know that the snark requires non-falsifiable assumptions or non-black box reductions, still we want to minimize the component in our construction, which requires non-falsifiable assumption. And here we use it for the minimal task of proving that the commitment is well-formed. And from a practical perspective, this gives us an alternative framework of constructing a snark, which could be efficient and competitive with the existing approach. So, right. So what do we know about FC schemes? Well, before September 2022, then when we want to build an FC for some classes of functions, and if we are allowed to use snarks for MP, then we can trivially get FC for circuits. So that's rather boring. But as I said in the previous slide, this requires non-falsifiable assumptions and it's not very satisfying. And so if we stick to falsifiable assumptions instead, then over the years, we managed to construct FCs for ever more expressive functionalities. So it's ranging from linear functions to semi-sparse polynomials, constant degree polynomials, or even NC1 circuits. Now, this is sufficient for bootstrapping a snark, but for the purpose of building a VC scheme, we want our FC to be as expressive as possible. So this year, there are 3 concurrent works which build functional commitments for circuits, for general circuits. So namely, there was the work of DeCastro and Packard and the work of Wee and Wu, who built functional commitments for bounded depth circuits. And in contrast, in this work, we built functional commitments for bounded width, but unbounded depth circuits. So let me summarize our results. First, we propose a new notion called chainable functional commitments, which is a generalization of functional commitments. So CFC in short. And we show how we can chain multiple CFCs for quadratic polynomials to get a CFC for unbounded depth circuits. And moreover, we give 2 constructions of CFC for quadratic polynomials, one from pairing assumptions and one from lattice-based assumptions. Both are falsifiable. And in particular, in the pairing setting, we built it from a new assumption called the hinted kernel assumption, which we prove to be true in the generic group model. And in the lattice setting, we built it from a twin version of the crisis assumption recently introduced in crypto Trinity. And subsequently, it has been shown that this twin crisis assumption is actually equivalent to the crisis assumption. And finally, as a corollary, we obtain homomorphic signatures for unbounded depth circuits. Okay, so in the remaining of this talk, let me walk you through the first 3 points. So let me introduce what a chainable functional commitment is. And for that, let us recall functional commitment first. So as I said before, it consists of 5 algorithms: set up, preprocess, commit, open, and verify. And here I want you to pay attention to the open and verify algorithm. So because an FC is supposed to capture the functionality that you have a committed input X and you open this commitment with respect to gamma to an output Y. So this function gamma has a single input. So this is reflected in the opening algorithm, which takes as input only one single auxiliary input. And correspondingly, the verify algorithm takes one commitment as input. And also we notice that the verify algorithm takes the output Y in plain text as input. And in terms of security, we have evaluation binding, which says that it's infeasible to open gamma and the commitment to 2 distinct Y and Y prime. And so generalizing FC, we get CFC. And basically, there are 2 changes. First, in FC, we have only a single committed input X, but in CFC, we have M committed inputs, X1 to Xn. And this is reflected in the open algorithm, which now takes M auxiliary inputs. And also the verify algorithm now takes M input commitments. And the second change is that the plain text output Y is now also committed. So we can see this in the verify algorithm, which now takes an output commitment instead of the output Y in plain. So we can observe that an output commitment can itself be used as an input commitment for further opening. So that's why a chainable functional commitment is chainable, as its name suggests. Okay, so let us see this chainability in action, or namely how we can build an FC for circuits from a CFC for quadratic polygons. So suppose we are given a depth D circuit, gamma, and an input. So the first thing we do is to partition the circuit gamma into multiplicative layers, gamma 1 to gamma D, where each gamma I is quadratic. And we can compute the values of the intermediate layers as follows. So first we set the input layer x0 to be just the input x, and we compute x1 to be gamma 1 of x0, x2 to be gamma 2 of x0, x1, and so on and so forth, until we reach the output y, which is xd, which is gamma d of x0 to xd minus 1. So to produce a CFC opening of gamma and a commitment of x to the output y, the prover would do the following. So first they commit to the intermediate layers, namely x1 to xd. And then for each layer I, the prover would produce a CFC opening for gamma I and the input commitments of x0 up to xi minus 1 to the output commitment of xi. So we can easily see that the evaluation binding of the resulting FC for circuits follows straightforwardly from the evaluation binding of the CFC. Okay, so next let me say a little bit about our CFC constructions from pairings or lattices. So for the interest of time, this is just going to be a very high-level overview. So a commitment is basically an inner product between a commitment key and the message in Peterson style. And an opening proof is some sort of pre-image of some quadratic functions of the commitments. So now, since a commitment is just an inner product between a commitment key and a message, when we multiply two of them together, we get a lot of cross terms. And the difficulty that we solve in the construction is to manage these cross terms so as to avoid unwanted collision. And we solve this by introducing three types of commitment keys. We call them type alpha, beta, and gamma. And we can think of the type alpha as the main type. So to prove a quadratic relation, for example, Z equals F times X tensor Y, where the matrix F and the type alpha commitments of X, Y, and Z are available to the verifier, the prover would first give a type beta commitment of Y and a type gamma commitment of Z. Then they open F and type alpha commitment of X, type beta commitment of Y to the type gamma commitment of Z. And then to complete the circle, the prover would prove that the two commitments of Y and the two commitments of Z are consistent. So for those of you who are interested, you can go through this slide, which is, I think, a bit easier to read than the paper. And so let me conclude this talk by taking this opportunity to advertise that we are hiring 2 PhD students in lattice-based crypto, and the job ad will appear in the ICR job box soon. Thanks.
Any question? If there are no questions, then let's thank Rother again.
Okay.
Okay. The next talk is multilinear short GP mod N and logic-based succinct arguments, and Benedict will give the talk.
Thank you. This is joint work with Ben Fish. So we've already seen some definitions of zero-knowledge succinct non-interactive arguments. but I want to focus on two things. We have the security properties, the soundness properties. We sometimes have some zero knowledge properties, but we also have efficiency properties, and we can roughly separate them into the succinctness property, which says that the proofs, we can construct these arguments with succinct proofs, so the proofs themselves are short. And also the other one is a verifiable computation property, which says that the verifier itself is very efficient. I want to focus in this talk on two particular variants of these so-called, sometimes called folding protocols, or these are variants, very similar protocol to the bulletproof protocol. The bulletproof protocol is a succinct proof that works in discrete logarithm groups, and it suffices, or you can build a polynomial commitment from it, which is a specific type of functional commitment, and that itself then can be used to build snarks. However, there's two downsides of these arguments in these discrete logarithm groups. One of them is that they're not secure against quantum computer. They rely on the discrete logarithm assumption. And the other one is that they have linear verification. However, there are alternatives. So it turns out that we can construct a very similar type of argument using lattice assumptions. So this is sometimes referred to as lattice bulletproofs. And it has one of the benefits is that it's plausibly secure against quantum computers. However, it also has some downsides. In particular, it has fairly low soundness. And the reason for that is that we only know how to instantiate it using a small polynomial-sized challenge set. And in order to deal with that, we have to repeat the protocol multiple times. That blows up the proof size. And also, naively, this protocol is an interactive protocol, but we might want to compile it to a non-interactive protocol using the Fiat-Shamir transform. And for protocols that have repetition, this becomes slightly more difficult. I don't want to go into details, but it basically becomes more difficult, and I might have to have even larger proofs. The other one is an argument that works in groups, so-called groups of unknown order. So this is, for example, the RSA group that is secure under the factoring assumption. And we had a work in 2020 called DARK that has one key benefit, which is that the verification time can be logarithmic in the statement. So unlike the bulletproofs argument in discrete logarithm. However, it also had a major downside, which is that it was broken. And in particular, the scheme itself is not necessarily broken, as we'll see in this talk, but there was a significant gap in the security proof, which was found by Block et al. And they fixed the protocol. However, their fix also involved using small challenges, in particular using binary challenges, which again then blows up the size of the proof. So the results that we're going to show in this paper is that we can show security of both of these protocols using exponential challenge sets. So we can now, instead of having to use small challenges and repetition, we can actually show that these protocols are secure, even if you use an exponential challenge set. And also we can do this using a unified treatment of both of these protocols. And this relies on two new results. One of them is a new Schwarz-Zippel lemma, modulo composites, so not just over fields, but modulo arbitrary composites. And then the other one is a new style of soundness notion that allows us to leverage this Schwarz-Zippel lemma, which we call almost special soundness. So let's look at the protocol, and let's look at a very simplified version of this bulletproof folding compression, which is that in each round, the prover sends two commitments, the verifier sends a challenge, and then somehow you take some random linear combination of the witness. And in the folding protocol, you do this for multiple rounds, but really it suffices to look at this simple sigma protocol. So when we want to analyze the security of this protocol, there's a very nice and natural, or there's a very nice soundness notion, which is called special soundness notion. Here is the multi-round variant of it, but basically it just says that I can extract from k different transcripts. And importantly, these transcripts are correlated in that they all have the same first message, but they have different challenges. And then if I want to extract this from, extend this to multiple rounds, then basically I can build this tree of transcripts where the challenges in the first round and the messages in the first round are the same, but then they diverge. So how do we prove that this protocol is special sound? Well, this is actually two special sound. So we just need two transcripts, the red one and the green one. And it turns out then using a simple, the difference between the prover messages and the difference between the challenges, we can compute one of the witnesses, and then it's easy to compute the other witness. This is easy to verify. So the protocol has special soundness, but what if we try to transfer this to a lattice setting? So let's try to do kind of the same style of analysis. Again, we have two transcripts. However, one problem here is that suddenly we cannot invert anymore. Things are not, we're not in a prime order group anymore. So we cannot simply invert the challenges, which doesn't allow us to compute the witness directly. However, one thing that we can compute is we can compute basically this relaxed opening what this is we can compute an opening to a multiple of the commitment. So R1 minus R2 is the difference of the challenges, and we can compute an opening to the differences of the commitments. And in fact, we can bound the size of this opening by 2 to the lambda. So it's lambda bits. However, if we try to extend this to multi-round protocols, well, let's look at this generalization. So let's look at a compressed sigma protocol for short openings, and we generalize this a little bit to arbitrary homomorphisms, and we basically want to show that there's a short preimage f of this homomorphism. And shortness we'll define this a little bit later. But the way that the protocol works is that in every round, the prover sends some commitments and the verifier responds with some challenge. And then in the final round, the prover sends an opening to the commitment, and the verifier can check the commitment opening and also verify that this final opening is a small integer. However, if we extract it from this using 2 to the mu special soundness, so basically a binary tree of depth mu, then we can compute an opening. We can compute, well, in fact, we can compute one of these relaxed openings. So we can compute an opening, so the original commitment is C, and we compute an opening of n times C. However, the problem is that the bit length of n, or that is going to be lambda times n. So the bit length, or basically the size of n that we extract is exponential in the original message length of the message vector that we've committed to. Yeah. So this is a problem because it basically then means that we have to use a commitment scheme. So we have to use a commitment scheme that is secure even or that has a binding property, even if T is very, very large. So basically it turns out that the size of the commitment, so these commitments are still binding for these relaxed openings, and we can show that. However, the problem is that the larger parameters I want it to be binding for, the larger my commitment has to be. So concretely, this would imply that my commitments are linear. The bit length of my commitment is linear in n, and then suddenly my protocol is not going to be secure anymore, is not going to be succinct anymore, because every single commitment that I send is now linear in n, in the bit length. Okay, so how have these previous works dealt with that? Well, what they did is they used exceptional sets or special sets where all the differences of the challenges are invertible. So why does this help? Well, if the differences of the challenges are invertible, then basically I can extract something that is not necessarily a rational opening, and then I can bound the size of this slack parameter, this B parameter. And one very simple example is just this challenge set 1 and 0. There are slightly better sets than that you can use. You can use sets of polynomial size, but all of them are still going to be of polynomial size, and we actually have an impossibility result that implies that it's unlikely that with these sets we're going to do much better than that. And the problem is that this, because we only have a polynomial size challenge set, this means that the soundness of one iteration of the protocol is lower, which means we need to use repetition, which increases the proof size and also has issues if we try to apply Fiat-Chemie. So one interesting question is, and this is, the gap in the security proof in this dark paper was also very much related to exactly this issue of extracting rational openings. However, does this mean that these protocols are insecure? Well, this does not directly correspond to an attack. But what if we think about, let's take the adversarial perspective. Let's take the attack perspective. So if we consider an honest prover, then what the honest prover does, it commits to some vector f. And then at the end of this protocol, it sends this final opening. And it turns out that this final opening corresponds to some polynomial f, which is actually the multilinear evaluation of the original vector that I committed to, evaluated at the challenges. So f is a multilinear evaluation or is a multilinear polynomial, and it is evaluated at f. And we know that in order to generate an accepting transcript, f evaluated at these challenges must be a small integer because the verifier checks this challenge. So what if the prover now tried to use a rational polynomial in the beginning? What if the prover in fact committed to a rational polynomial? So we can write this as some polynomial g of x, some integer polynomial g of x divided by some numerator n. So if we see this, what this implies is that still the adversary, if it wants to succeed, needs to output an integer at the end. So what this means is that we know that g evaluated at the challenges divided by n has to be a small integer. So g of x has the coefficients g. However, if we think about it, if n is very, very large, it's actually it seems unlikely that this thing is a small integer. So how do we formalize this notion? Well, this is what we need to show is that g evaluated at these challenges divided by n is a small integer. And this is equivalent to saying that g evaluated at these challenges is equal to 0 mod n. However, we know n is not if n was a prime, our life would be easy because then we could apply the Schwarz-Zippel lemma, but we have no idea whether n is a prime. We have no prior information about what n is. However, so what we did is we developed a new Schwarz-Zippel lemma that works modulo composites and shows that if n is large enough for any n, this probability is in fact negligible. The other problem is that special soundness does not capture this perspective. So if we look at this statement carefully, this is a statement about the claimed witness G and the set of challenges. However, this doesn't really make sense because in special soundness, we use the challenges to extract the witness, right? So G certainly doesn't seem to be independent of the challenges. So what does it mean here that the challenges are run randomly? So in order to capture this notion, we had to define a new notion called almost special soundness, which implies knowledge soundness. I'll use the last 2 minutes to talk about this new Schwarz-Zippel lemma. So in the classical de Milo-Lipton-Schwarz-Zippel lemma, this was invented multiple times, it says that a multivariate polynomial is equal to 0 mod some prime. This probability is negligible in lambda if I sample my variables from 0 to 2 to the lambda, and p is larger than 2 to the lambda. So this holds more generally for f over fields and integral domains. However, this does not hold for arbitrary commutative rings, and it's actually fairly easy to come up with counterexamples. So for example, if I show that f of x is equal to 0 mod p, then if f of x is equal to p times x, then for every second value of x, this polynomial is going to be 0. So this does not hold it generally. And even if we restrict to f to be coprime mod n, it turns out that for higher degree polynomials, this doesn't hold. But this does leave multivariate, so it doesn't hold for higher degree polynomials, it doesn't hold for, and we require that it's that the polynomial is coprime. But what we're able to show is that for multilinear polynomials, coprime with n, we can actually show that the probability is going to be negligible in the size of the modulus. So yeah, my time's up, and I encourage you to read the paper, and thank you very much.
So unfortunately, we don't have a time for question. So please ask question offline. So let's thank Benedict again. So the next talk is generalized spatial sound interactive proofs and their novelty soundness. And Thomas give you a talk.
Thank you. So this is joint work with my co-authors, Serge and Nick. So we will be considering interactive proofs, which you all know for sure, but let me quickly introduce them. So these are interactive protocols between a proofer and a verifier, when a proofer claims to know a secret witness W for a given public statement X. And after some interactions, rounds of interactions, the verifier either accepts or rejects this claim. So interactive proofs have several desirable security properties, but we will be focusing on knowledge soundness. And informally, this states that dishonest proofers almost never succeed. So a dishonest proofer without knowledge of the secret witness W will not be able to convince a verifier with large probability. More formally, knowledge soundness is defined in terms of this knowledge extractor. And what does a knowledge extractor do? A knowledge extractor receives as input this public statement X and oracle access to a prover P star attacking the protocol. And its goal is to extract a witness W for the public statement X. And we say that an interactive proof is knowledge sound if it admits a knowledge extractor with large enough success probability and expected polynomial runtime. So it's typically non-trivial to prove knowledge soundness. You have to construct this extractor. So for this reason, more than 25 years ago, an alternative notion called special soundness was introduced. Benedict already mentioned this notion. And it is typically much easier to prove special soundness than knowledge soundness directly. So special soundness was originally defined in the context of Sigma protocols, which are 3-round interactive proofs. And suppose we have such a 3-round interactive proof in which the second message from the verifier to the prover C is sampled uniformly at random from a challenge set of size n. Then we say that such a Sigma protocol is 2 out of n special sound if you can extract a witness W efficiently from 2 colliding protocol transcripts. And 2 transcripts are colliding if they have the same first message A, but different challenges C and C prime. It is well known that 2 out of n special soundness implies knowledge soundness with knowledge error 1 over n, which matches the typical cheating probability, or the trivial cheating probability for typical Sigma protocols. So there are some natural generalizations you can require. For instance, instead of 2 accepting transcripts, you can require k of them. Then you also get knowledge soundness with knowledge error k minus 1 over n. And there's also several. There's also a multi-round generalization of this notion that was presented in the presentation before. And in this multi-round version, you need these 3 of transcripts to extract. I will be focusing for simplicity on the 3-round setting. So Benedict already mentioned a couple of drawbacks or limitations of this special soundness notion. And I will mention a couple of others and generalize this notion in another direction. So let us see where things go wrong. There are namely many interactive proofs for which you require additional structure to extract. So in some sense, the special soundness notion is a threshold notion. It states how many transcripts you need to extract, but sometimes you need a bit of additional structure. A very simple example is this standard amortization technique. So suppose we have this proof of knowledge where the prover claims to know n different pre-images for the homomorphism psi. And what this protocol basically does, it amortizes the complexity of the trivial n-fold the n-fold repetition of the standard Sigma protocol. So instead of proving knowledge of all the n pre-images one by one, it proves knowledge of a random linear combination of this random linear combination of the public values. So this is a very simple example, but what do you need to extract? You need a bit of additional structure. You namely need n different transcripts such that the challenges, C1 up to Cn, the bold-faced ones, which are now actually vectors, form a basis of your challenge space Z3 to the power n. Now, if we try to capture this by this threshold special soundness notion that we know, we see that we require q to the power n minus 1 plus 1 transcripts to extract. Because only if we have at least q to the power n minus 1 plus 1 accepting transcripts, then we know with certainty that they must contain the basis of this challenge space. Well, this property is useless because typically q is exponentially large, so this will render your knowledge extractor inefficient. So another example, I will not treat this one in detail, is a simple protocol for opening Merkle tree commitments. I just want to mention that this is an example that you encounter when you compile, for example, PCPs or IOPs into interactive proofs. And also here we typically end up with inefficient knowledge extractors. And there are several other examples, natural examples, where you run into this problem. And what we did in this work is we define a more general notion of special soundness, capturing the above examples and some more. We construct a knowledge extractor for interactive proofs that satisfy this property. And we also generalize to multi-round interactive proofs. We get a parallel repetition theorem almost for free. And then we apply this to a non-trivial example, which is the Fry protocol, which is an interactive verbal proof. So what do we do exactly? We define these monotone access structures, gamma, which are sets containing subsets of the challenge set. And all that we require is that this gamma is monotone, which basically means that if A is contained in gamma, then any set B containing A is also an element of gamma. And this is quite a natural notion in our context, because if we are able to extract from, say, A, then we are most certainly also able to extract from B. So then we say a 3-round interactive proof is gamma spatial sound if you can extract from colliding transcripts A, C1, Z1 up to A, CK, ZK, where the first message is the same and the challenges C1 up to CK form an element of your access structure. So to give some examples, a K special soundness, then of course you get a special access structure where gamma contains all the subsets of large enough cardinality. For the amortization technique that I described, you need the span of S to, so that gamma contains all subsets that span the entire challenge space. And for this Merkle tree IP, it's also relatively easy to define the corresponding access structure. So then what we need to do next is construct a knowledge extractor for gamma special sound interactive proofs. And we do this by making the following observation. And that's basically at any stage of the extractor, the challenge set can be partitioned into a set of useful and useless challenges. Typically, these extractors work by rewinding the proofer several times. And every time the proofer is rewinded, you try to extract an additional challenge or an additional transcript. And with a new challenge. And some of these challenges give you new information and others won't give you any new information, and these are we call useless. So more precisely, we denote this by this function u gamma of A, where A denotes the challenges that you've already found, and u gamma A will then denote the subset of challenges that are remaining that will still be useful to you. So some examples for this threshold access structure. Any challenge that you haven't found yet will remain useful. For this amortization technique, you will try to find challenges that are outside of the span of the challenges that you've already found. And similarly for Merkle tree IPs. So you have to be a bit careful in defining this notion of useful subsets or useful challenges. This is the formal definition, but let's not spend too much time on this. Let's just write down some of the natural properties. So for instance, challenges that you've already found will never be useful. Further, this set of useful challenges is decreasing. So if you find more transcripts, then the challenges that remain, the set of challenges that remain useful grows smaller. And finally, if you've already found accepting transcripts for a set in your access structure, then there are no useful challenges remaining. These are quite natural challenges or properties. So then the main idea is actually quite simple. To find the ELT transcript, so somewhere in the extraction process, you simply rewind and sample a new challenge from the set of useful challenges. So we do this by adapting previous extractors. Again, you have to be a bit careful because for some extraction procedures, this approach fails, but fortunately for others, this approach works and everything comes together. What is important in the analysis is this crucial parameter, T of gamma, which nicely captures the refinements that we made. So this T of gamma defines the length of the longest sequence of useful challenges that you can find. And the expected running time actually grows linear in this parameter T of gamma, which basically means that knowledge soundness is implied. So gamma spatial sound interactive proofs are knowledge sound if T of gamma is polynomial. Now, this is a crucial parameter in the analysis and also when you apply these techniques. So to briefly summarize the implications of this result, we see here that we can always define this threshold spatial soundness parameter K of gamma. And now we have this refined parameter T of gamma. And we see, for instance, that if we look at the amortization technique, the parameter T of gamma is much, much smaller than K of gamma, where K of gamma was exponential, T of gamma is simply n. And the same holds for the other examples given here. Another example that was mentioned earlier this week was the notion of local spatial soundness. Also, local spatial soundness can be captured by this more general notion of gamma spatial soundness. So to briefly summarize, in this presentation, I introduced this more general notion of spatial soundness together with some of the tools to analyze it. And I claimed that it implies knowledge soundness. Well, in the paper, you can find the actual knowledge extracted together with the analysis. In the paper, we also have a generalization to multi-round interactive proofs. We have the parallel repetition theorem and the application to the Fry protocol, the interactive oracle proof. I must admit that there are some limitations when applying this extraction procedure to the Fry protocol. We have a discussion on that in the paper as well. Follow-up work will handle, for instance, the natural question, what happens if you take a Fiat Shamir transformation of these protocols? This will appear soon on ePrint. And a remaining open question is how to improve our Fry extractor. There are some directions that we could explore. Thank you. I think there's still time for some questions.
Any question? Then let's thank Thomas again. The last talk of the last talk to this session is a merge of two works. One is from polynomial IOP and commitments to non-malleable Bernard snarks, and the other is how to compile polynomial IOP into simulation extractable snarks, a modular approach. And Luigi and Mahak will give the talk.
Well, thank you. So, yeah, we're going to be talking about both of these works. And both of these works study non-malleability of zero-knowledge snarks that are obtained by compilation process from polynomial interactive oracle proofs. And the approach is going to be to identify easy to verify properties from polynomial commitments, which form the core part of the compilation scheme, and the PIOP. As an implication, we get a slight variance of Planck, Marlin, and Lunar when compiled with the KZG commitment scheme are non-malleable. So why do we want to study simulation non-malleability? Because the standard definition under which we safeguard against a correct prover is via knowledge soundness, which, like the previous talks mentioned, it says that a correct prover cannot come up with a proof without knowing the witness. But notice that in this definition, there's a single tuple of statement and proof, and in particular, it doesn't talk about more proofs. But realistically, a correct prover probably gets to see multiple proofs and can launch a malleability attack where it just takes a previously generated proof, mauls it, and outputs that without knowing the witness. So now you cannot extract from that. For that, we need to go to a stronger definition called simulation extractability, which implies non-malleability. And here the prover gets this additional power of seeing multiple proofs via simulation queries. And then later, we ask the extractor, we require that the extractor should still be able to extract a valid witness from an accepting proof. So this problem has been studied in the past for existing succinct snarks. And the gap in all of these approaches is that even though they try to provide a generic enough framework, the analysis at the end of the day is still very specific to the protocol. So a question that we try to answer in both of these works is, well, is it possible to claim non-malleability for a large class of existing snarks without having to go into the details of each of these proof systems? And to do that, because we want to answer it for a larger class of zero-knowledge proofs, we look at a common paradigm of making these proofs, which is via compilation of PIOPs. So, right, so you design an information theoretic proof system called a PIOP, and then you compile it using a knowledge sound commitment scheme, polynomial commitment scheme, and then to get non-interactivity, you put Fiat Tremere on top, and that gives you the final knowledge sound ZK star. And we want to look at this because there's a long line of snarks that are built using PIOP. And in particular, we want to look at the KZG commitment scheme because that's the scheme that's used by a lot of these papers for the final compilation. So just a little bit about how this compilation works. In the PIOP setting, the prover wants to prove a statement, and to do that, he comes up with these polynomials and puts them as oracles in the sky. And in return, the verifier sends some challenges back. And this can happen for a bunch of rounds, towards the end of which they reach the query phase, where the verifier can query these oracles for evaluations. And that's modeled as a query algorithm that takes input as all the challenges, and then outputs which polynomials should be evaluated at what point. And the verifier can evaluate them directly from the oracles. To compile it, the prover, will commit to these polynomials using a polynomial commitment scheme, which allows you to commit to polynomials and then later open evaluations to them along with proofs of correct evaluations. And then obtain challenges from the random oracle, and then towards the end, it would output the evaluations and also these proofs of correct evaluation. So the transcript consists of all the commitments, challenges, evaluations, and the proofs. And for this approach, we took different approaches to get to the same result. The first one that I will be talking about follows a proof template from previous papers that attempt to do the same thing. And this template works for other proof systems other than just PIOP-based ones. And here you want the proof goes as follows. If the underlying ZK snark is knowledge sound, has chapterless zero knowledge, and satisfies some variant of unique response, then that would imply simulation extractability. But the difference here is that all of the prior works look at the final result of ZK snark, and here we will try to look at the smaller pieces, PIOP and the commitment scheme, and identify properties from these objects. And the variant of unique response that we would use is called weak unique response, which I'll explain what that is later. And the second approach is a more direct one. So notice that the knowledge soundness of ZK snark is tied to the knowledge soundness of commitment scheme. So if you could come up with a notion of simulation extractable commitment scheme, then that would maybe give you simulation extractable ZK star. So the second approach is to come up with this new notion for the commitment scheme. All right, so I'll talk about the first one, and then Luigi takes over to talk about the second one. So here, the goal is, so this is the template that we want to show. And I will not talk about knowledge soundness because that's typically proven. I will talk about how to generically show chapterless zero knowledge and weak unique response, and then basically fill this table for PIOP and commitment schemes. So chapterless zero knowledge just means that, the zero knowledge simulator doesn't need any chapters for simulation. It can observe and program random multiple queries. And one of the theorems that we have in the paper is a very basic one, says that if your PIOP has honest verifier zero knowledge and the commitment scheme is hiding, then that gives you chapterless zero knowledge for the compiled ZK-SNAR in a generic way. And both of these properties are standard and you show them anyway while giving the PIOP and commitment scheme. And we have a second theorem in the paper, which works for weakly hiding commitment schemes, which allow you to leak some information about the committed polynomial. So for instance, deterministic commitment schemes. And to get chapterless zero knowledge for that, we define a stronger notion of honest verifier zero knowledge. So basically, we say that if there is some randomness to begin with in the PIOP, then you don't need randomness in the commitment scheme. And for the final property, weak unique response, that means that an adversary cannot reuse a simulated transcript. So it cannot come up with a transcript which shares a common prefix with a simulated transcript. And then the ith prover message is different. To show this, the properties that we identify here, the first one is we need that the PIOP has high min entropy for the query algorithm. So recall that towards the end of the PIOP, there's a query algorithm that takes in input as the challenges and outputs what should be evaluated. And we say, we define this as, if you change the inputs, if you change one of the challenges, then it changes what should be evaluated. And we need a second property, which is just that the first polynomial shouldn't be evaluated at all distinct points, like all degree plus one distinct points, which just means that don't reveal the entire polynomial in the open to the verifier. From the commitment scheme, we need the standard hiding and binding, and unique evaluations proofs, which is not the most standard property, but for KZG scheme, we show it in a very simple way that, yeah, it satisfies it. And similarly, we have a second theorem which works for weakly hiding commitment schemes and then requires some additional properties from the polynomial IOP. And yeah, so that's the end of my part.
Thank you, Mark. So even though we wanted to achieve a similar goal, we took a different perspective, as Mark was saying. So let's recap again the usual transformation from PIOP to SNARK using polynomial commitment and Phil-Shamir. What we can observe is that the derived ZK SNARK is not always simulation extractable. For example, let's assume that we use a polynomial commitment, which is fully malleable. In theory, one could transform a simulated proof, which is just a proof over a bunch of commitments, into another proof. So yeah, we cannot extract it. We cannot extract a witness from this. So we took this other approach. So let's try to see if we require some stronger property at polynomial commitment level. Do we achieve then simulation extractable ZK SNARKs? Well, in theory, it could be possible, but this would not capture existing constructions because we know that polynomial commitments like KZG, they cannot be simulation extractable because they are malleable. So KZG is this very famous polynomial commitment. It works on bilinear groups. The structured reference string is a tower of powers for a secret point S. In order to commit, you just compute the polynomial in the second point. The evaluation proof is the quotient polynomial committed. And in order to verify, you just need to check that the quotient polynomial multiplied by the secret point minus the evaluation point is equal to the commitment shifted by the evaluation value. And you can check this just using two pairings. KZG is linearly homomorphic, so it's also malleable. Just consider two simple malleability attacks. Given a proof pi for a commitment C opening to a point X to a value Y, the proof pi is also a valid proof for other commitments. For example, the commitment C shifted by any constant delta when open to in the same point X, but to the value Y plus delta. And we can also use pi on arbitrary point X star. So we may derive a commitment as C minus the quotient polynomial multiplied by X star minus X. And this is a valid proof on the point X star. The fact is that even though these are malleability attacks to KZG, these are not sufficient to break the simulation extractability at SNARK level. This is true if the PIOP is what we define compiler safe, so that all the PIOP polynomials are evaluated on the last round coin of the verifier. So we cannot require then a polynomial commitment to be fully simulation extractable, but maybe we can require some policy-based simulation extractability, which is just a generalization of the usual simulation extractability experiment. And we identified a policy that is both sufficient for this compiler to work, but also met by KZG. What is this policy-based simulation extractability? Well, just take the usual experiment in which the extractor needs to extract, but then let's prepend a very simple if clause. So if the policy is satisfied, then the extractor must extract. We already have a lot of such policy-based simulation extractability in the literature. For example, this weak simulation extractability. There is a constraint at extraction time. So the extractor needs to extract only if the statement is fresh, or we can have constraints at simulation time. So the adversary is only allowed to ask simulations for true statements. And the policy under which we prove KZG to be simulation extractable falls in the algebraic model and the random oracle model. It has some simulation constraints and extraction constraints. As for the simulation constraints, we require the adversary to choose a set of points, and then you can only ask simulations on these points. So this can be arbitrary, but non-adaptively chosen. And we also require some form of what we call algebraic consistency. So for example, on the same commitment in the same point, the adversary cannot ask for two proofs to two different values, evaluation values y. Instead, for the extraction constraint, we require that the point X star on which the extractor forges needs to be sufficiently random and also chosen after the commitment C star. Well, we also need to make some extra adjustments to this to the original recipe, because the PIOP does not only have to be compiler safe, but we require the verifier to be non-adaptive and algebraic. So in particular, this means that the queries of the verifier are independent of the statement. And also we require the existence of a commitment simulator. So there exists a way to a strategy, a way to simulate that is linear with respect to a vector of simulated commitments. This is basically given for free when the commitments are hiding, or may require some computation assumption if not. And these two constraints are actually very easy to meet in practice. For all the PIOPs that we looked at, these were met. Now, to wrap up, the reason why on this stage you have seen two people and not just one presenting a joint work, our two approaches achieve similar goals, but there are also a lot of differences. So in particular, as Mark was saying, they require, they assume that a trapdoor-less simulator, while we rely on a trapdoor simulator. They derive the weak unique response property from the unique proofs of polynomial commitments. So for example, they analyze the case of KZG, while we require the stronger property from the polynomial commitment. And this also means that while their approach was in a way easier for KZG and does not require the AGM, our approach was somewhat more involved, and also it strongly leverages the flexibility of the algebraic group model. As for concrete schemes, while they capture Planck only with hiding commitments, we are able to capture Planck even with deterministic commitments. We also share some common limitations. So in particular, we are not able to capture Marlin and Lunar as they are described in the original papers, but just slight variants of these protocols. We both require programmability of the random oracle, and we are not able to capture the fully optimized IOPs. So in particular, the ones that are actually deployed in the real world. For example, there is this Moller trick or linearization trick that we are not able to capture. Even though these seem like open problems, there is some ongoing work on basically all of these 3 bullet points. So hopefully they will be fixed soon. Thank you, everyone. We are here for questions.
Yeah, very nice works. I guess I had 2 questions. One was regarding the last thing you said. Do you think there's any chance that these protocols are actually malleable or not? And
Which protocols?
like you said that the like Marlin or Lunar is described in the paper, you're not able to prove that they're simulation extractable or things that use this linearization track. Is it possible that they're actually malleable or do you think it's just our techniques are not good enough yet?
No. We do not capture them at the current level with the current work, just because we made some simplifying assumptions. But the ongoing work that we have on Marlin and Luna seems to confirm that they are not malleable. They are simulation extractable under some constraints. In particular, you cannot use every polynomial commitment to prove that Marlin and Luna are simulation extractable. So, for example, on the just to make an example with Marlin, you cannot use hiding commitments in the last round of Marlin.
Okay. And then the other question is, so both of these approaches work for polynomial IOPs, but is it, do you think similar techniques would work for, like functional IOPs with then a functional commitment? Like does this sort of this same pipeline, should that work as well?
Well, I can only talk about the upper side.
Yeah.
I think it would, but I think everything should be, again, modeled and syntactically changed to capture different notions
Right.
and polynomials. Yeah.
Very cool.
Just maybe one minor. Yeah, I think we also looked at some other IOP models, like the one in which use multilinear, for example, polynomials. We do not have results on this, but yeah, there is some intuition that we may use or reuse some of these work.
Any other question? This is the end of the session and all the talks today. So let's thank all the speakers again.
Conference announcement. Okay, so I'm Yuran Huang, and I'm in the conference like for participant and also like